Good afternoon, everyone. So, I welcome you all once again for the problem solving session for this NPTEL course, that is Computational Fluid Dynamics. And the course code is NOC25CH18, and we are into week 9, where we have been solving all problems related to that week's assignment. So, it will be helpful for you guys when you submit the assignments on time, because assignments carry certain weightage of your final marks. So let me introduce myself. So I am Ankara. So I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad, and the course instructor is Professor Sreenivas Jayanti sir from the Department of Chemical Engineering, IIT Madras. So the session will start from 3 p.m. to 5 p.m. and I'll give you an introduction. In the meantime, let others join and we will go into the problems. So the course layout and things will be repetitive for if you are listening every week, but if you are just a new learner, it will give you an idea. So that's why I included it in every week's slides. So this computational fluid dynamics course is a 12 weeks course. So we are covering from what is basics to what is required for us to master the CFD. And for that, in the first week, we have seen about the introduction to the calculation of flow in a rectangular duct, followed by the calculation of fully developed flow in a triangular duct. So in the first week, we have seen about flow fields through the, getting flow fields through the finite difference approach, and second week it is about finite volume approach. And in third week, it is about derivation of equations governing fluid flow. And this is like for continuity equation and 3 momentum conservation equations. Because when we are talking about fluid flow, what we mean is that we are solving those equations and getting the solutions. Getting analytical solution is the most difficult task, so we are going with the numerical methods and getting the solutions by using the computational resources. So for that, we need to identify what equations we would be solving. So the first step is that we are solving about continuity and momentum conservation equations when there is no external heat transfer or mass transfer. If there is additional heat transfer, we will be solving additional heat transfer equations, and for additional mass transfer, or we will be using species balance when if chemical reaction is taking place. So all those things will come into picture additionally. Next is about equations of for incompressible flow and boundary conditions. In addition, we have seen about the boundary conditions as well, which is like we specify certain values along the domain geometry, so that it will help us get the balanced system of equations and the number of unknowns, so we can solve it and get exact solution. So these boundary conditions can be like either values in Dirichlet boundary condition, or we can even specify it as the value. If it is the value to a variable, we call it Dirichlet boundary conditions. If we specify value to the derivative, we call Newman boundary condition. And next is about basic concepts of CFD, finite difference approximations. And week 6, basic concepts of CFD, consistency, stability and convergence. So finite difference approximation, we have been using it. We have derived it from the Taylor series approximation and got the approximations for the derivatives. And also we have seen how when we are solving equations, we need to ensure certain conditions like consistency and stability. Only then we can get a converged solution. So those things are also there. And in the last 2 weeks, we have seen about solution of Navier-Stokes equations And last before week we have seen about solution of Navier-Stokes equations for compressible flows, and in the last week we have seen about the solution of Navier-Stokes equations for incompressible flows. So basically what we have seen is that for compressible flows we have methods like McCormack scheme, beam warming scheme, and so on. Whereas for the incompressible flows we have pressure correction method, artificial incompressibility method, and steam function vorticity approach, and so on. So like those methods also we have seen. And in today's week we are going to see about the solution of linear algebraic equations basic methods. So basic methods like direct method, iterative procedures. So we are going to see about them in today's class. Today we are going to deal with problems dealing with that particular thing. And in the next week it will be about solution of linear algebraic equations advanced methods, and week 11 it is basics of finite volume method including grid generation, and finally we will be seeing about turbulent flows and turbulence modeling. So this is the idea for the 12 weeks course layout. So the course theory is actually covered by the professor in his videos, and that is available to you. Like I hope you have covered the theory aspects from that. These sessions which are handled by myself will include the problems and solutions related to that particular week's assignment to aid you in submitting the assignments and clearing your doubts if any. So for books and references we have almost 5 books. First one is Firziger J.H. and Perick M. 1999 Computational Methods for Fluid Dynamics, Springer, Berlin, Germany. Hirsch C. 1988 Numerical Computation of Internal and External Flows, John Wiley and Sons, New York. And third one Patankar S.V. 1980 Numerical Heat Transfer and Fluid Flow, Hemisphere, Washington DC, USA. And last it is Versteeg HK and Malalsekara 1995 An Introduction to Computational Fluid Dynamics, The Finite Volume Method, Longman Scientific and Technical, Harlow Essex UK. Anderson JD 1995 Computational Fluid Dynamics, The Basics with Applications, McGraw-Hill Inc. So these are the 5 books and references. So now we will move on to problems for week 9. So in week 9, as we have seen, it is about the solution of the linear algebraic solution to linear algebraic equations using the numerical methods. We are going to see about the basic methods. So what we do in CFD, we discretize the domain geometry into smaller grids, and in each grids we solve the equations like continuity equations, momentum conservation equations, and so on. And what are all these equations? These equations are partial differential equations. So we need to identify a method which will ensure we get the solution for the variables. So we are using the numerical techniques because analytical approach isn't not possible to get the solution for this. So for ease of computation, we are going with the numerical techniques. So first we are going to see about the basic methods in this week, and later we will see problems related to advanced methods. So first one, it is about so we have a few theory few, okay, I'll remove this. So first we will read the question and later we will answer the questions. So first question, what is given? You wish to solve the Poisson equation in a two-dimensional domain spanning a length of L in the x direction and width W in the y direction. We have divided the length into L into 20 equal intervals and with W into 30 equal intervals. You have non-zero Dirichlet boundary condition on all sides. You discretize the Poisson equation using central difference approximation of second order accuracy. The source term is a constant. You wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Ax is equal to Q. For this problem, answer the following questions. So what is given? We are asked to solve the Poisson equation in a two-dimensional domain. So the domain is looking like this. It is a two-dimensional domain and we are talking about x and y. This is x and this is y. So in x we have length L into 20 equal intervals and width W into 30 equal intervals. And we are applying non-zero Dirichlet boundary condition on all sides. What is Dirichlet boundary condition? We are giving the value to the variables. For example, if it is some temperature related problems, we are giving the value of temperature on all the values which is non-zero values. Non-zero Dirichlet boundary condition on all sides. You discretize the Poisson equation using central difference approximation of second order accuracy, and we have source term in the Poisson equation which is a constant. Here in this problem it is a constant. So you wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Ax is equal to Q. So we are discretizing it and we have the source term as constant and we wish to solve the resulting set of linear algebraic equations. So now we have to answer the questions. Before that, I will just give you an idea. Where is my cursor? Okay, it is here. I'll give you a small idea. Alright, this we have seen in the previous class itself, but just to give you a reminder. So this, let us consider this is L. Alright. Now we are dividing it into 1, 2. Okay, we'll keep it like this. I mean, just ignore my cross drawings, but apart from that, I think you're getting my idea, right? And similarly, ignore the extension as well. Eraser. We are dividing x into 1, 2, 3, 4, 5, 6. 6 equal divisions and y into 1, 2, 3, 4. 4 equal divisions. Alright. Now we need to know how many points we are getting. So we are getting 1, 2, 3, 4, 5, 6, 7. 7 points here. So yeah, there was slight thing issue from my end. So we'll continue now. So as I mentioned, like here it is divided into 5. Okay, we'll change it to into 5. Okay. Okay, let it be 4 only. It is 4 and now how many points we got? We got 5 points. Alright, we got 5 points here. So what do we mean? If we are dividing it segment into 6 equal divisions, we are getting 6 plus 1 7 grid points. Similarly, 4 equal divisions, we are getting 4 plus 1 5 grid points. And what thing we need to know is all these external thing will go as boundaries. So how many are we left with? We are getting with 4 equal divisions, we are getting 1, 2 and 3. 3 points. So 4 minus 1. Similarly, for this direction, we got 7 points, but we are leaving out 2. So 7 minus 2, 5. So again, 6 divisions, we are leaving out 1. 6 minus 1 is 5. So how many have we got? 6 minus 1, 5 into 3. It should be 15 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15 points. So we got 15 interior grid points. So that is the statement. Now we will see the questions. So that is to give you an idea of how we are going to solve our problems. So now when we are going to look at our problems, what have we got? We have got question 1, which is stating something like, which of the following equations is an appropriate governing equation for this problem? Which of the following equations is an appropriate governing equation for this problem? Options are, okay, first one, it is dou f by dou t plus a into dou f by dou x plus b into dou f by dou y equal to 0, where a and b are greater than 0. Second one, dou f by dou t equal to gamma into dou square f by dou x square plus dou square f by dou y square plus c, where c is greater than 0. And 3, it is gamma into dou square f by dou x square plus dou square f by dou y square plus d equal to 0, where gamma and d both are greater than 0. And last, it is gamma into dou square f by dou x square plus dou square f by dou y square plus e equal to 0, where gamma is greater than 0 and e is less than 0. So these are the 4 equations, and we need to identify which of the following equations are an appropriate governing equation for this problem. So in the question statement, what was given? It was given as Poisson equation. So Poisson equation is of the form dou square f by dou x square plus dou square f by dou y square equal to f into xy. We have a source term in Poisson equation, and in this question it is given as a constant. So rest other terms remain the same. Dou square f by dou x square plus dou square f by dou y square. So that if we are looking at, we have 3 and 4 as our requirement, whereas 1 and 2 has something like dou f by dou t. So this is not present in our the equation, because in source term it is given as a constant, and therefore we can ignore 1 and 2 statements. So for third and fourth equations are in our desired form. So we look at it. Options are option A 1, option B 2, 1 and 2, option C 4 only, option D 3 and 4. So we already saw how 3 and 4 equations are only suitable for our system. So option D 3 and 4 is the right answer. We will just see how that is. So in the question it is given as Poisson equation. Also we know that Poisson's equations are elliptic equations, elliptic partial differential equations. So they are not time varying, they are like time independent solutions. So it is given as del square phi equal to f into xyz, where phi can be any function. So it is dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square equal to f into f of xyz. So in two-dimensional domain, what will we get? We will get it as dou square phi by dou x square plus dou square phi by dou y square equal to f of x and y. This is for the equation for us in two-dimensional domain. And final answer is therefore we have 3 and 4 equations, right? If we look at third equation, it is given as gamma into dou square f by dou x square plus dou square f by dou y square plus d equal to 0. So this gamma should obviously be positive for us to get in the desired form, and d can be positive or negative. It doesn't matter. So if d is positive, it is third equation. Similarly, here in fourth equation, what have we got? We got it as gamma into dou square f by dou x square plus dou square f by dou y square plus equal to 0. Here e is less than 0. So either it can be positive or it can be negative, but gamma should be positive always. So therefore 3 and 4 equations are our desired equations. So I'll give you guys 1 minute time. Just look at the equations and analyze it and understand it carefully. Alright. Now we will move on to next question. Question 2. In question 2, what is given? Poisson equation is an example of dash. Option A, hyperbolic equation. Option B, parabolic equation. Option C, elliptic equation. Option D, it is of mixed character. So in the last slide itself, we have seen that Poisson equation is an example of elliptic equation. So answer to this problem is elliptic equation. I'll tell you how. Poisson equation is an example of elliptic equation. So, elliptic partial differential equations are characterized by having no time dependent terms, and the solution typically describes steady equation or equilibrium conditions. So, elliptic equations are time independent, that is they have no time dependent terms. So, dou t by dou t, dou f by dou t, all those terms will not be present, and the solution typically describes steady state or equilibrium conditions. So answer is elliptic equation. And if we look into it more clearly, Poisson equation is elliptic in nature. It is like del square phi equal to f of x and y, dou square phi by dou x square plus dou square phi by dou y square equal to f of x comma y. This is the Poisson equation in two-dimensional domain. Before that, I'll give you an I'll give you this. So B here is 0. The general equation is written as general PDE A plus B by dou by x dou by dou square phi by dou x dou y plus C plus D equal to 0. So in our equation, A equal to 1, B equal to 0, C equal to 1. Equal to 1. We need to identify B square minus 4AC. And what is it giving? B square, B is 0 minus 4 into A into C equal to minus 4. So here it is elliptic. So Poisson equation, here it is dou square phi by del square phi equal to f of x comma y, and we have the generalized equation as dou square phi by dou x square plus dou square phi by dou y square equal to f of x comma y for the two dimension. So the general PDE can be written as A into dou square phi by dou x square plus B into dou phi by dou y x dou y plus C into dou square phi by dou y square plus D equal to 0. And for our equation, if we are using this formula, I mean using this to the comparison, we are getting B as 0, A and C as 1. So we need to identify the nature of the equation. So for that, what we should do is we need to calculate b square minus 4ac. If b square minus 4ac is less than 0, it is elliptic. If it is greater than 0, it is hyperbolic. If it is equal to 0, it is parabolic. I repeat, b square minus 4ac, if it is equal to 0, it is parabolic. Equal to 0, parabolic. Less than 0, it is elliptic. Greater than 0, it is hyperbolic. So in our case, what we are getting b square minus 4ac as b is 0. So 0 minus 4 into a into c. Minus 4 we are getting. So since it is less than 0, it is elliptic. I hope it is clear now. If you want, take a minute. We will see the next problem then. Alright, now we will move on to next problem, that is question 3. In question 3, what we got is that for an interior point, how many terms involving f at I comma j will have non-zero coefficient values in the discretized equation? For an interior point, how many terms involving f at I comma j will have non-zero coefficient values in the discretized equation? Option A 3, option B 5, option C 7, option D none of the above. So for an interior point, how many terms involving f at I comma j will have non-zero coefficient values in the discretized equation. So we are talking about interior points, not at the boundaries and not even closer to the boundaries. So it is in the interior points. So how many we will get? We will get maximum 5. Because consider this, if we are talking about this point, we will have this point, this point, this point, this point and this point. The chances of all these terms to be non-negative, non-zero, I mean not non-negative, non-zero is there. So we will have 5. So answer is option B. 5 is the answer. How? We are saying it is, our equation is dou square f by dou x square plus dou square f by dou y square equal to C. We are discretizing using the central difference scheme and we are getting it as f at I minus 1 comma j and minus 2 times of f at I comma j plus f at I plus 1 comma j divided by delta x square plus f at I comma j minus 1 minus 2 times of f at I comma j plus f at I comma j plus 1 divided by delta y square. So here we are going with I minus 1 and I plus 1 variation in the x domain. Here it is variation in the y domain equal to C, because in the question it was given that the source term is constant for this particular problem. So it is C. So if we look at it, we have 1, 2, 3, 4 and 5 terms. So the 5 terms can be non-zero. So that is why the answer is option B, 5. I hope it is clear. Question 3 is clear, I guess. Just take a look at it. So we'll move on to next problem shortly. If you have any doubt, you can stop me and ask the question. Okay, we'll now move to the next question. In question 4, before going to question 4, I'll just explain you how the terms we use to talk about the 2D mesh. This is a two-dimensional mesh. So here we have cells, and the center of cell we call as cell center, and the corner points we call it as nodes, like this one, intersection of points we call it as nodes, and this one where it is common between two cells we call it as cell face, and if it is along the boundary we call it as boundary face, and this one element is cell. One element is cell, points are nodes. If it is at the center, it is cell center. If it is if face is lying along the cell, it is cell face. If it is along the boundary, it is boundary face. Now coming back to question 4, we have the question like the number of equations to be solved will be dash. Option A around 550, option B around 600, option C around 650, option D around 100. So we need to identify how many equations we will be solving. So we will be solving the number of equations that is equal to the number of unknowns. So simply if we take a look at it, here the mesh is divided into 4 cells in the x direction and 4 cells in the y direction. So we have got 1, 2, 3, 4, 5. 5 nodes in x direction and 5 nodes in y. Sorry, 5 nodes in x direction and 5 nodes in the y direction. So the corner nodes are boundary. So we need to exclude those. We need to get only these. So it is 5 minus 2 because we are excluding boundaries. So we will get 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 5 minus 2 and here again 5 minus 2. So 5 minus 2 is 3, 3 cross 3, 9. 9 grid points we will be getting. So number of equations to be solved will be 9 for this particular case. Similarly, if we take a look at the larger picture, what will we get? We will get the number of equations to be solved. So answer is around 550 is the answer. We will see that how. Because we are dividing the length into 20 equal intervals and the width into 30 equal intervals. So if we apply the same concept from here to there, what will we have? We will have, it is 4 divisions 4 minus 1. 4 divisions 4 minus 1 or number of grid points, number of nodes minus 2 or number of cells, number of intervals minus 1. Okay. So here it is number of intervals. So 20 intervals minus 1 into 30 intervals minus 1. So it is 20 minus 1 into 30 minus 1. So here it is 19 into 29. 20 minus 1 into 30 minus 1. So 19 into 29. So what does 19 into 29 give? It gives us 551. So therefore we are giving the answer as around 550. So number of equations to be solved is 20 minus 1, number of intervals minus 1 into width, number of intervals minus 1 in the width direction. So it is 20. Okay, it is reverse. 19 into 29, whatever. So I hope it is clear. Similar thing what we saw here only we applied here. Here number of intervals is 4. We are getting 3 interior points. Similarly number of grids is 4. We are getting 3 interior points. So it is 20 minus 1 into 30 minus 1. 19 into 29. It should be 19 into 29 but I think it is okay. Which gives us 551. So if it is, since it is 551, we are giving the answer as around 550. So option A is the right answer. Option A is the right answer. If you want, you just take a minute and observe the problem and later we will move on to next problem. So in today's class, how the division is that based on the problem statement, we will see 5 problems and we will have one more problem statement in 3-dimensional domain. We will have some problems from that as well, and finally we will have some generic math numerical method related questions. Alright, now we will go to question 5. Question 5 is again something related to it. What is being asked, we will see. In question 5, percentage of elements in the coefficient matrix A having non-zero value will be of the order of dash. I repeat, percentage of elements in the coefficient matrix A having non-zero value will be of the order of dash. percentage of elements in the coefficient matrix A having non-zero value will be of the order of dash. So as we talked about, we are having these equations, and this equation, how will we discretize? We discretized it, and we will write it in the form of an equation, and we will rearrange it in the form of a matrix, that is in the form of Ax is equal to Q, where x is the grid points. So it will be like number of equations. So the number of equations 551. So here x is of the order of 551 cross 1, like it is a column vector, and we have A matrices. A matrix is a square matrices of the order number of equations into number of equations. So it is a square matrix. So it is 551 cross 551. So that is the total size of the A matrix. So in this A matrix, we need to identify the percentage of elements which are having non-zero values. So it is of the order of dash. We will look at the options first. In the option, it is given option A, it is greater than 99 percentage. Option B, it is less than 0.01 percentage. Option C, it is around 1 percentage. Option D, around 50 percentage. So I talked about the matrix A, right, which is having the size as 551 cross 551, and we are asked to find the percentage of elements in that particular matrix which is having non-zero values. So here we are asked to find what is the percentage of elements in A which are non-zero. So simply that is the question. So how will we find out? For that we need to know which will be zero elements or which will be non-zero elements. We need to have a rough estimate. So we'll see that, but on looking at it, we can say it is around 1 percentage. So option C is the right answer. I'll give you how to calculate in the next slide. So here it is question 5 answer. We will see how we got around 1 percentage. So we need to know how many percentage is, before percentage we need to know how many elements are non-zero, right? So it is our equation in two-dimensional domain is dou square f by dou x square plus dou square f by dou y square equal to C. We are discretizing it as follows. F at I minus 1 comma j minus 2 times of f at I comma j plus f at I plus 1 comma j divided by delta x square plus f at I j minus 1 minus 2 times of f at I comma j plus f at I comma j plus 1 divided by delta y square equal to 0. So number of equations to be solved is 29 minus 19. 30 equal divisions in I think width direction and 20 in the length direction. Something like, but it is 30 cross 20 domain. We are getting the number of equations to be solved as 30 minus 1 cross 20 minus 1. That is 551. So total number of elements in the coefficient matrix is, as I said, it is 551 cross 551. So it is 3,03,601. So the interior grid points will have a maximum 5 non-zero elements. Interior grid points. So I'm not talking about points next to this. I'm talking about interior points. Like this is boundaries. We already left it. And we are dealing with only these points, and of these points I am leaving out the layer next to the boundary. I am talking about the innermost points. So the interior grid point will have maximum 5. So 5 elements are present, 5 terms are present, and the chances of 5 points to be non-zero is there. So interior grid points will have maximum 5 non-zero elements. So how to identify how many uh, interior grid points are there? If we talk about here, we are excluding 1, 2, 3, 4. So 4 divisions, 5 grid points, and of that 5 we are subtracting 1, 2, 3, 4. So we are subtracting 4. 5 minus 4 or 4 minus 3. So we will be having only one grid point, interior grid point. So in our case it is 30 minus 3 or 29 minus 2. Here how I have taken is 29 minus 19, right? So this is 29 grid points and 19 grid points. So in that I am subtracting 2. Like how it is 3 minus 2. So 3 points are there under our consideration. Of that we are subtracting 2. 29 minus 2 into 19 minus 2. These many interior grid points will have 5 non-zero elements. So we are counting 5 non-zero elements for these points. So it is 29 minus 2 into 19 minus 2 into 5. Because 5 non-zero elements are present in the interior grid points. So we are getting it as 459 into 5, that is 2295. Clear? Up to this I hope it is clear. So what are we doing? First we are discretizing the equation and we are identifying the at most the equation will have 5 non-zero element because it is a two-dimensional domain. And total number of equations to be solved, we got it as number of divisions minus 1 into number of divisions minus 1 in both the directions. So it is 30 minus 1 into 20 minus 1, which we are getting it as 29 into 19. So the total number of elements in the coefficient matrix will be the square of this because it is a square matrix. So it is 551 cross 551. Now we need to know which grid point will have maximum 5. The innermost grid points will have maximum 5. That is excluding the layer next to the boundary. So we are excluding the layer next to boundary and we are getting it as 29 minus 2 into 19 minus 2 into 5. So it is 459 into 5. So it is 2295 points will have maximum 5 non-zero elements. So we will keep this aside. Now we need to know how many elements will be present in the layer next to the boundary. Grid points next to the bottom and top wall will have 4 non-zero elements. Grid points next to the top and bottom wall will have 4 non-zero elements. Again here I am excluding the corner node points. So it is, so how many will be there? So here if we are excluding these points, I am talking about this point, this point, this point, this point. Again it will be 29 minus 2. Okay, we are talking in the other length direction. So it is 19 minus 2. 19 minus 2 and we have two layers, bottom and top. So into 2. Into 4. They will have 4 non-zero elements. So that is coming as 136. How did we know they have 4 non-zero elements? Because they have one adjacent boundary layer. So one, for example, if we take this itself, as I mentioned, I am talking about this point. This point will have one boundary. So it can be from it is y boundary. Yeah, it is in the y dimension. So here it will have 1, 2, 3, 4. 4 values, 4 non-zero values. Similarly for this point it will have 1, 2, not 1. This is boundary, it will go 1, 2, 3 and 4. 4 non-zero values. Grid points next to the top and bottom wall will have 4 non-zero elements. So it is 19 minus 2 into 4 into 2 because we have bottom wall and top wall. So it is into 2. So here we have 136 elements. Now similarly for the left and right wall will again have 4 non-zero elements. So we are calculating as 29 minus 2 into 4 into 2. That again gives us 216. So we have covered bottom wall, top wall, left wall, right wall and interior points. What are we left with? We are left with the corner node points 1, 2, 3 and 4. These grid points will have how many non-zero elements? It will have 1, same point, 2 and 3. 1, 2 and 3. We will exclude 1 and 2 here. These two will go in the boundary. So we have 1, 2 and 3. So corner points next to the boundary will have 3 non-zero elements. So we have 4 corner points on the whole. So it is 4 into 3, that is 12. So these are the uh, non-zero elements, number of non-zero elements in the coefficient matrix. So here we have 12, 136, 216 and there was one more 2000 something. So the total number of non-zero elements is 2295, 136. This is interior points. This is bottom and top wall. This is left and right wall. And this is a corner grid points. So when we sum up all this, what we have is 2295 plus 2016 plus 136 plus 12, which is summing up to 2659. So the total number of non-zero elements is this. When we divide it by total number of elements in the coefficient matrix, we will get the fraction. So in order to get the percentage of elements in matrix A having non-zero value, we are dividing 2659 divided by the total number of elements in the coefficient matrix into 100. So it is 0.8 percentage. So this is the 0.8 percentage. So now it is 0.8 percentage, around 1 percentage. Therefore the answer is around 1 percentage. Option C, around 1 percentage is the right answer. So I hope it is clear for you. I'll just put this for 1 minute. Just see to it that you understand everything. Alright. Okay. What we'll do is that now the time is around 3:56:57. So, okay. I'll keep this slide and we'll take a 2-3 minutes break. We'll come back by 4 and we'll solve the problems again. Alright, we'll start now. So, as I mentioned, now we are going into three-dimensional problem. So it is similar problem statement, but it is in a three dimension. What is given in the statement is that you wish to solve the Laplace equation in a three-dimensional domain spanning a length L in the x direction with W in the y direction and height h in the z direction. You have divided the length into 40 equal intervals, width into 30 equal intervals and height h into 25 equal intervals. You have Dirichlet boundary conditions on all sides. You discretize the Laplace equation using the central difference approximation. You wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Ax is equal to Q with lexicographic ordering of equations. For this problem, answer the following questions. I repeat the question once again. You wish to solve the Laplace equation in a three-dimensional domain spanning a length L in the x direction, width W in the y direction and height h in the z direction. So what we are doing, we got a three-dimensional domain, L in x direction, W in y and height in z. And we are dividing the length into 40 divisions, width into 30 divisions and height into 25 divisions equally. And we are using the Dirichlet boundary conditions, which is specifying the value of the variable along the boundaries. So along the boundaries, the number of elements will be reduced along, like a layer next to the boundaries will have a number of elements will be less. So now we are discretizing the Laplace equations. So here we are solving for Laplace equation. In previous question it was Poisson equation and here it is Laplace equation. The difference between both the equations is that in Laplace equation we have source term as 0. You discretize the Laplace equation using central difference approximation and we are solving the resulting set of linear algebraic equations which we are arranging in the lexicographic ordering of equations. So this is the statement. Same statement as the last problem. Only thing we are doing is we are solving for Laplace equation here and we are doing it in a three-dimensional domain. So it is an extension to the previous problem. So what are we doing? We are dividing the x domain into 40 divisions, y domain into 30 divisions and z domain into 25 divisions. So that's it. Now we need to solve the resulting set of linear algebraic equations. So keeping in mind this problem statement, we have to answer the coming up questions. So read this question once again carefully. We will move to the questions. Read the statement once again carefully. Okay, now we will move to the questions. Okay, just to give you an idea, I am just giving the equations here. It is del square phi equal to 0 is the Laplace equation and del square phi is expressed as dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square. And Laplace equation, this is equal to 0 as I mentioned. Dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square equal to 0. Now we are talking about a simple three-dimensional mesh. So previously we saw simple two-dimensional mesh. Here we are talking about simple three-dimensional mesh. So here terminologies again remain the same, but in different way we are talking about. So one cell is again a three-dimensional cell. So this we call it as cell, and this entire thing we call it as face, boundary face, and the lines along it we call it as edges, and the points we call it as nodes. Points we call it as nodes, and this one is cell, and this is edge, and this is boundary face. So the terminologies are these. Now when we are moving on to the question, what we got here is that which of the following is are or true about matrix A? So again here we are actually discretizing it and writing it in the form of Ax is equal to Q. So A is the coefficient matrix. So which of the following is are true about matrix A? So option 1, statement 1, it will have 9 non-zero diagonals. 2, more than 99.9% of the elements of A will be 0. Third, it will satisfy the condition for strong form of diagonal dominance. These are the three statements that is given for us, and we need to identify which of these statements are true. So first statement we will look at it. It is given that it will have 9 non-zero diagonals. So A is a coefficient matrix, and based on the information provided we cannot talk anything about the non-zero diagonals because it is a huge matrix, that is one, and we are also not sure about what elements will be. We can have prediction, but the structure of thing is not a diagonal matrix. I'll tell you, it is not a non-zero, it is not a diagonal matrix first of all. And second statement, more than 99.9% of elements will be 0. This is true because in the last problem itself we have seen that how it is around 1% of elements of A were non-zero. That was for two-dimensional case, and for three-dimensional case it is even more. So more than 99.9% of elements of A will be 0. So second statement is true statement. Third statement, it will satisfy the condition for strong form of diagonal dominance. It will satisfy the condition for strong form of diagonal dominance. Again, this is false because the elements present in it, it won't always satisfy the strong form of diagonal dominance, because along the boundaries, along the corner points, corner nodes, all these will have a different form of equation, so they will not account for the strong form of diagonal dominance or non-zero diagonal elements. If we are talking only about the interior most grid points, we can say something about a diagonal dominance or something else, but since we are talking about all the points inside the domain, the points next to the boundary, near the boundary, will have one less than the required boundary points, required elements. So all these things will play a major role, and also like it won't satisfy the diagonal dominance. We can make it, but it won't. So second statement alone is a true statement. So options are option A 1, option B 2, option C 3, option D all of the above. So the right answer is option B is the right answer. B 2 is the right answer. So we'll see how actually. How second statement is true alone we will see, because rest of the things we know. So we'll see how the number of elemental points is greater than elements having 0 is almost 99.9% and above. So now here Here it is not 2, it is 1. So the total number of grid points in our system is 40 plus 1 into 30 plus 1 into 25 plus 1. Because in the last thing itself here, if we talk about here also, we can say that it is 1, 2, 3, 4, 5. 5 equal divisions, and we have got 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. Including the boundary, we got 6 points. Similarly, if we talk about here, we are dividing into 3 divisions and we have 4 grid points including the boundaries. I am talking about inclusion of the boundaries. So it is plus 1. 3 plus 1 and similarly 5 plus 1. In the z direction also we can say similarly. So the total grid points is 40 plus 1 into 30 plus 1 into 25 plus 1. This is inclusive of the boundary points. So total grid points is 41 into 31 into 26. So we are getting 33,046. So the total number of equations which we need to solve now, we need to know it will account the interior points. So we need to subtract 1 from the total intervals. So it is 40 minus 1, 30 minus 1 into 25 minus 1. So it is 39 into 29 into 24. Or in other words, what we can do is 41 minus 2 boundaries, top and bottom or left and right. So 41 minus 2 is also 39, 40 minus 1 is also 39. It is all conceptual. Whichever way you go, it is right. So it is 40 minus 1 into 30 minus 1 into 25 minus 1. 39 into 29 into 24, which is giving us 27,144 number of equations. Total number of equations is this. This is total grid points. This is total number of equations. Now our Laplace equation is like this. Dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square equal to 0. And we are discretizing using the central difference scheme, and we are getting the equation as this. F at I plus 1, sorry, I minus 1 comma j comma k minus 2 times of f at I comma j comma k plus f at I plus 1 comma j comma k divided by delta x square plus f at I comma j minus 1 comma k plus minus 2 times of f at I comma j comma k plus f at I comma j plus 1 comma k divided by delta y square plus f at I comma j comma k minus 1 minus 2 times of f at I comma j comma k plus f at I comma j comma k plus 1 divided by delta z square. So here we are discretizing in the 3-dimensional domain. Accordingly, we are giving the point locations. And it is equal to 0 for the Laplace equation. What we should remember here is that we are having total number of points as 7. Total number of elements, total number of points is 7 in each equation. Okay. Number of interior node points, leaving out the nodes next to the boundaries. Number of interior node points, leaving out the nodes next to the boundaries, we will have 39 minus 2 into 29 minus 2. So this is the inclusive of the, this is the total interior points actually. Now we are just excluding the layer next to the boundary as well. So one more layer we are excluding, and we are taking only the interior most points. So it is 39 minus 2, 29 minus 2, 24 minus 2. And what will we get? We will get 21,978. 21,978. So interior node points, leaving out the nodes next to the boundaries, will have 7 non-zero elements. So interior points will have 7 non-zero elements. All the elements will be non-zero. So 7 non-zero elements. So it is 21,978 into 7, which is giving us 1,53,846. So this is the interior node points, leaving out the nodes next to the boundary points. And they have 7 elements, 7 non-zero elements. So the number of non-zero elements resulting from the interior node points is this. So now we have grid points next to the bottom and top wall will have 6 non-zero elements. That is, we are excluding one for the top and bottom boundary. So that will have 6 non-zero elements. So for top and bottom wall, we are again grid points next to the bottom and the top wall will be 40 minus 1 into 30 minus 1, and we have two walls. So here it is 2 and the number of non-zero elements is 6. So we are multiplying by 6. So here it is 2262 into 6, 13,572. Again we will have for the left and right wall, which will again have 6 non-zero elements. So it is 30 minus 3 into 25 minus 1 into 6 into 2. We are subtracting 2 because some layers will have common points, right? So we are subtracting 2 in this equation alone. So it is 30 minus 3 into 25 minus 1 into 16 into 2. So actually if you visualize, the corner layer will have repetitive points common for both. So we are just excluding those. In one equation we are excluding. So here front and back wall will again have 6 non-zero elements. So we will exclude from here as well. So 40 minus 3 into 25 minus 3 into 6 into 2. So 9,768. Here 7,776 and 13,572. So these are the total number of non-zero elements from the grid points in the layer next to the boundary. Corner points next to the boundary will have 4 non-zero elements because it will have 2 boundary values and 3 boundary values. I am talking about the exterior corner, so it will be enclosed by 3 boundaries. So 7 minus 3 will give us 4 non-zero elements. So total corner points will be 8. So it is 8 into 4, it is 32. So the calculations are somewhat approximate because certain points might be repeated. And total number of non-zero elements in A is therefore 1,53,846 interior points, 13,572 grid points along the boundaries. These are along the layer next to the boundaries, 7,776 and 9,768. And the corner node points we have 32, which is amounting to 1,84,994. So total number of elements in A will be square of the number of equations to be solved. So it is 27,144 square, which is giving us 73. Okay. 73 crores 67 lakhs 96,736 number of elements in A. And percentage of non-zero elements in A will be, these points we calculated are non-zero elements. So 1,84,994 into 100 divided by this value will give us 0.025. So percentage of zeros in A will be 100 minus this, which is 99.975 percentage. So it is above 99.9 percentage of elements of A will be 0. So that is our statement, and we have found it true as well. So that is why in the question we said second statement is true. More than 99.9% of elements of A will be 0. More than 99.9% of elements of A will be 0, which we have proved as well. So I'll give you 1 minute time. Just look at it. We will solve the next problem. If you have any doubts, you can ask. Okay, now we will move to next question, that is question 7. In question 7, what we have is that which of the following is or are true about the matrix Q? So we have divided, discretized the equations, and we have used the form as Ax is equal to Q, where A is the coefficient matrix and Q is the right hand side matrix. So we need to know which of the following is true about matrix Q. First one, it is a square matrix. Second one, all of its elements have the same value. Third one, all the elements are negative real numbers. Okay, we have three statements here. One is it is a square matrix. So when we talk about the form Ax is equal to Q, we know A is a square matrix and X and Q are column matrix. It is like a single column with number of elements equal to the number of equations to be solved. So it is not a square matrix. First one is false. Second one, all of its elements will have the same value. It is not true because Ax is equal to Q. In the original form, Q will be like in the equation, Laplace equation, we will have source term as 0, del square phi equal to 0. But after substitution of certain values, especially in the corner points or in the values next to the boundary layers, we will have some values and it will not be the same for all the elements. So again, second statement is false. Third statement, it is given all elements are negative real numbers. This is also false because these numbers are not negative. So all three statements are false. They aren't true. So we will see the options. Option A 1, option B 2, option C 3, option D none. So all the statements are false. Therefore none is the right answer. None of the above is the right answer. Option D none. So why we will see. Ax is equal to Q. The matrix A is the system of coefficients and vector Q is the right hand side. Matrix A is generally square as it represents the coefficients for a system of linear equations. Nature of Q, it is not square because it is a vector. It is a column matrix, column vector, and it is not a matrix, square matrix. All the elements of Q are not the same values. They are all different values in arising from substitution in the equation. All elements of Q are not negative or real numbers in general. So that is for question 7. Now we will move to question 8. Again we have the structure. In the coefficient matrix A, what percentage of number of rows will have the diagonal element to be equal in magnitude to the sum of magnitudes of the off diagonal elements. So I repeat the question. In the coefficient matrix A, what percentage of number of rows will have the diagonal element to be equal in magnitude to the sum of magnitudes of the off diagonal elements? So we will see the options. Option A, more than 99.9 percentage. Option B, about 99 percentage. Option C, about 90 percentage. Option D, less than 75 percentage. So here actually what we are asked is that we are asked to find the percentage of number of rows which will have the diagonal element to be equal in magnitude to the sum of the magnitudes of the off diagonal elements. So answer is actually 90 percentage. Option C is the right answer. How will we calculate? We will calculate it from the discretized equation of the Laplace equation. So Laplace equation we have, it is dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square equal to 0. So here if we discretize, if you remember the central discretization which we use, central scheme. So here they have 7 non-zero elements, and in that 7 the 1 and 2 1 and 2, like those repetitions were there. So the it will lead to the diagonal element to be equal in magnitude to the sum of the magnitudes of the off diagonal elements. So I'll show you how in the next slide. So but it answer is about 90 percentage is the right answer. So if we take a look at it, it will actually give us the interior grid points whichever we use will lead us to the answer that those will give the number of rows with diagonal elements equal to the magnitude, equal in magnitude to the sum of magnitudes of the all of diagonal elements. So here if we see the question 8 answer, what we have is that Laplace equation is of the form dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square equal to 0. And after discretization we are getting it as this, that is f at I minus 1 comma j comma k minus 2 times of f at I comma j comma k plus f at I plus 1 comma j comma k divided by delta x square plus f at I comma j minus 1 comma k minus 2 times of f at I comma j comma k plus f at I comma j plus 1 comma k divided by delta y square plus f at I comma j comma k minus 1 minus 2 times of f at I comma j comma k plus f at I comma j comma k plus 1 divided by delta z square. So when we take these terms like separately, we have f at I comma 1 comma j comma k divided by delta x square plus f at I plus 1 comma j comma k divided by delta x square plus f at I comma j minus 1 comma k divided by delta y square plus f at I comma j plus 1 comma k divided by delta y square plus f at I comma j comma k minus 1 divided by delta z square plus f at I comma j comma k plus 1 divided by delta z square minus 2 times of 1 by delta x square plus 1 by delta y square plus 1 by delta z square at f at I comma j comma k. So this f at I comma j comma k will become the diagonal element. These will become the off diagonal elements. So the magnitude of the sum of this is equal to the magnitude of the sum of this. So interior grid points will have the diagonal element to be equal in magnitude to the sum of the magnitudes of the off diagonal elements. So the magnitude of the sum of diagonal element is equal to the sum of the magnitude of the off diagonal elements. So here this is equal to the sum of all this in magnitude. So we need to now know how many interior grid points will be present in the coefficient matrix. So the number of interior grid points is that we already saw that it is a number of intervals minus 3. Like in this last problem, not in 7, in question 6 we have seen that number of interior node points is 39 minus 2, that is 39 is the number of we are just leaving out the nodes next to the boundary points as well, and we are taking only the innermost boundaries. So it is 39 minus 2 or 40 minus 3, however convenient we can write. 40 is the number of divisions, so it is 40 minus 3 into 30 minus 3 into 25 minus 3. Okay, so it is 40 minus 3 into 30 minus 3 into 25 minus 3. So it is 21,978. So 21,978 divided by the total number of rows will be 27,000 something. So 27,144 will give us 0.81. So it is 81 percentage. Along with this, some of the elements near the boundary layer, next to the boundary layer, might also lead to this. So that will add some more. So final answer would be like around 90 percentage. Sorry, about 90 percentage. Like 81 percentage plus some more might arise from the boundary elements, near boundary elements as well, and it will lead to total 90 percentage. So it is not exactly 90 percentage, it is about 90 percentage. So answer is option B, sorry, option C. Option B is 99 percentage, so answer is option C. In the coefficient matrix A, what percentage of number of rows will have the diagonal element to be equal in magnitude to the sum of magnitudes of the off diagonal elements? So answer is option C, 90 percentage, about 90 percentage is the right answer. Now I hope question 8 is clear. Now we will go to question 9. In question 9, what is asked is that if you have divided the length into 50 equal intervals with W into 40 equal intervals and height H into 30 equal intervals, the number of equations to be solved will be dash. So in the previous questions, we have seen the division as 40, 30, 25. So in this question, what is asked is that we are dividing the domain into 50 equal intervals in the length, 40 equal intervals in the width direction, and in the height Z direction we are dividing into 30 equal intervals. So for this we need to identify the number of equations to be solved. So similarly, how we have seen in this particular figure itself, we can take we will have 1 2 3 4 5 equal intervals, sorry, 5 equal intervals and 3 equal intervals. So from 5 equations, for whichever the points, we will leave out the boundaries. So it is 1 2 3 4, 5 minus 1, 4 points along the y, and if in the z in the x we will have 3 equal intervals and we will have 2 points because 2 more falls in the boundary. So it is 3 minus 1 2, and similarly in the z direction we are having 4 equal intervals and we will be having 3 points, 4 minus 1. So the number of equations which we will be solving for this simple system is 4 into 3 into 2. 4 3s are 12, 2s are 24. 24 equations we will be solving. Similarly, if we apply the same concept to our larger system, that is length 50 intervals with 40 intervals and height 30 intervals, we will get the number of equations. That is 50 minus 1 into 40 minus 1 into 30 minus 1. So options are option A close to 55,000, option B close to 50,000, option C close to 27,000, option D less than 25,000. So answer is option, okay. We will first calculate it. So the number of equation is, as I mentioned, it is 50 minus 1 into 40 minus 1 into 30 minus 1. So the total number of grid points in the domain will be the number of intervals plus 1 will give the total number of grid points. Number of intervals plus 1. The total number of points excluding the boundary points will be number of intervals plus 1 minus boundary points, minus 2 boundary points something. So it will be number of intervals minus 1 plus 1 minus 2. So it will become minus 1. Number of intervals minus 1. So number of equations is 50 minus 1 into 40 minus 1 into 30 minus 1. So that is giving us 55,419. So the number of equations to be solved is 55,419. So of the options, it is coming close to option A. So option A, close to 55,000 is the right answer. One good thing with these problems is that you can give an approximate solutions. You are not asked to provide the exact solutions. It is close to 55,000. So there might be some repetitive points in the thing we are doing. So it won't affect your final answers. You are just asked to give closer values. So that's it. Answer to question 9 is option A, that is close to 55,000. This is the number of equations which we will be solving. So the total number of elements in the domain will be 55,419 into 55,419 will give us the total number of elements in the matrix A. That I think we are clear enough now. So this is for this. Now we will go to next question. Question 10. In question 10, we have, which of the following methods can be used to solve the system of equations Ax is equal to Q described above? So we are, as mentioned, we were solving, we are back into the original problem statement, and we are asked to discretize a Laplace equation, and we were arriving at A in the form of Ax is equal to Q, where A is the coefficient matrix and X is the unknowns and Q is our just matrix. So it is a column vector as we have seen. So we need to now know which of the following methods can be used to solve a system of equations. First one, the TDMA scheme, that is tridiagonal matrix scheme or the Thomas algorithm. Second one, Gaussian elimination. Third one, LU decomposition. So our method actually did not produce any diagonal matrix form. So TDMA is false. Like we cannot use it for this particular system, but we can use Gaussian elimination and LU decomposition. So we will look at the options first. Option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So answer is option B 2 and 3. Because tridiagonal matrix algorithm we cannot use, because our the matrix, the resultant matrix Ax is equal to Q, in that the coefficient matrix A did not have any tridiagonal matrix scheme, I mean matrix format. One thing is, we are not only concerned about the interior grid points, but we are also including the boundary points, I mean points next to the boundary layer. So the points next to the boundary layer will have 1 less or 2 less or 3 less, something with respect to how many boundaries it is covering. So that will reduce the total number of elements in that particular term, non-zero elements in that particular equation. So it will not finally produce, why I am telling this, it will not lead to any structure in the matrix finally, like tridiagonal matrix. So we cannot go with TDMA scheme, but we can go with the Gaussian elimination and we can go with the LU decomposition. 2 and 3 are true. We will see that. Okay, 2 and 3 are true. Now coming back, we have question 11. In question 11, diagonal dominance condition is required for which of the following methods? Diagonal dominance condition is required for which of the following methods? Option A, Gauss-Seidel. Second one, LU decomposition. Third one, TDME, tridiagonal matrix algorithm. So we'll look at the options. First, diagonal dominance condition is required for which of the following methods? So we will see the options. Option A, it is 1. Option B, it is 1 and 2. Option C, it is 1 and 3. Option D, it is 1, 2 and 3. So when we are talking about diagonal dominance, Gauss-Seidel requires diagonal dominance condition to be maintained. Otherwise, the method will not converge. So first one requires diagonal dominance condition to be met. LU decomposition does not require diagonal dominance condition because it is simply dividing the matrix into lower matrix and upper matrix. So it doesn't require the diagonal dominance condition. Whereas 3, that is tridiagonal matrix algorithm, also requires the diagonal dominance condition to be met. So answer is option C is the right answer, that is 1 and 3. How it is that I'll just give you a brief idea. So in Gauss-Seidel method, it is an iterative method. Gauss-Seidel is an iterative method. So it requires the diagonal dominant condition to be met. Gauss-Seidel is an iterative method used for solving linear system of equations. For Gauss-Seidel to converge efficiently, the matrix should ideally be diagonally dominant. That is, the magnitude of the diagonal element in each row should be larger than the sum of the magnitudes of the other elements in that row. That is, the magnitude of the diagonal element should be greater than the sum of the magnitude of other off-diagonal elements in the row. Only then the Gauss-Seidel will lead to converged solution. Second is, diagonal dominance is ensuring convergence for the method, particularly when we are dealing with a very large matrix and so on, sparse matrix where number of zeros are too high. So in those cases, we must ensure diagonal dominance condition is met for us to get a converged solution. Second one, it is LU decomposition. In LU decomposition, what we are doing is that we are dividing, it is a direct method to solve the system of linear equations by decomposing the matrix A, that is Ax is equal to Q, that elemental matrix, coefficient matrix A, into lower and upper triangular matrices. LU decomposition does not require diagonal dominance. It works as long as the matrix is non-singular, meaning the determinant is non-zero. Like as long as it is non-zero, determinant of matrix A is non-zero, LU decomposition works. So diagonal dominance is not necessary for the LU decomposition. Third method is tridiagonal matrix algorithm. TDMA or tridiagonal matrix algorithm is an efficient method used to solve the system of linear algebraic equations where the matrix is tridiagonal. Only we have main diagonal and 2 adjacent diagonals which will be 0, and we will use forward elimination and backward substitution to get the solution. Like Gauss-Seidel, TDMA benefits from diagonal dominance for stability and convergence, especially in iterative methods. So since it is like TDMA is also like similar to Gauss-Seidel, in TDMA also the convergence is easily met when we ensure diagonal dominance, because only 3 elements are present, like the diagonal element, subdiagonal element and the above diagonal element. So it can be done. Diagonal dominance helps ensure stability and convergence for this method also. So diagonal dominance is necessary for Gauss-Seidel method and tridiagonal method. So answer was 1 and 3. Option C, 1 and 3 is the right answer. Gauss-Seidel and TDMA, tridiagonal matrix algorithm. Now we will go to question 12. In question 12, sorry, what we have is that in question 12, you wish to solve a set of equations Ax is equal to Q using Jacobi method. Which of the following conditions must be satisfied by the coefficient matrix for the method to work? So what is asking is that we are using Jacobi method to solve our final form, that is Ax is equal to Q, and we are asked to find which of the following conditions must be met, must be satisfied by the coefficient matrix A for the method to work. So what is Jacobi method? It is like a similar to Gauss-Seidel method, only that in Gauss-Seidel method you will be updating the values, whereas in Jacobi method it will use values from the previous iterations. So since it is similar to Gauss-Seidel method, what is must? Diagonal dominance condition is must for Jacobi method. So when we talk about the options, we have option 1, first one, it is matrix A is non-singular. Second one, matrix A is irreducible. Third one, matrix A is diagonally dominant. Okay, all three are actually required conditions to be satisfied by the matrix A, that is the coefficient matrix A, for the method to work. So we will see that how in the next slide. Before that, options are option A 1, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So answer is option D is the right answer, that is 1, 2 and 3 is the right answer. Option D 1, 2 and 3 is the right answer. How we will see now. So we are now talking about the Jacobi method. As I mentioned, it is similar to the Gauss-Seidel method. So from Gauss-Seidel method, we know very clearly that diagonal dominance condition is a must criteria. So similarly for Jacobi method also, diagonal dominance condition is a must. Two other thing is matrix A is non-singular, matrix A is irreducible. So first one we will see matrix A is non-singular. For the Jacobi method to work, matrix A must be non-singular. That is, it should have an inverse. So only then it can work better. If A is singular, that is its determinant is 0, then the system of equations Ax is equal to Q either has no solution or an infinite number of solutions, and the Jacobi method cannot converge in such cases. So it is an iterative procedure, right? Jacobi method and Gauss-Seidel method, everything is an iterative methods. Everything are iterative methods. So we need to get a converged solution at one point. For us to ensure convergence, matrix should be non-singular. What do we mean by non-singular? The determinant should be non-zero. If in case its determinant is 0, we cannot inverse it. That is another story. But if it is non-zero, if it is 0, if A is singular, that is its determinant is 0, then the system of equations will have no solution or infinite number of solutions, both of which is not our requirement. We need an exact solution, true solution. So Jacobi cannot converge in such cases. Non-singularity is a fundamental requirement for any iterative method to ensure there is unique solution. To ensure there is a unique solution on a non-singularity is a must. Matrix A is irreducible. That is the second criteria. So irreducibility of a matrix means that matrix cannot be put into block upper triangular form by permuting its rows and columns. So what is irreducibility? Irreducibility means that like it cannot be put into like upper triangular form by permuting its rows and columns. So it is also a must criteria. And finally, it is diagonally dominant. Diagonal dominance is an important condition for ensuring the convergence of Jacobi method. Matrix is said to be diagonally dominant if for each row absolute value of the diagonal element is larger than the sum of the absolute values of the other element in that row. So this we have seen last thing itself. Diagonal dominance, actually what it does is it ensures we will get the converged solution for a broad class of problems. If problem is very large, we will have a converged guarantee that we will have a converged solution. If not, the matrix, the solution might be running in loop and we will not be getting a solution, and it is a time waste and resource waste as well. So these three criteria, that is, it should be non-singular, it should be irreducible, it should be diagonally dominant. That is matrix A, that is Ax is equal to Q, where A is the coefficient element matrix. So these are the conditions the matrix must meet to get the converged solution. So that is for question 12. Now we will move on to question 13. Question 13 states that norm of the residual at the end of m iterations can be evaluated as dash. First one, the largest value in the magnitude of b minus ax at m. Second one, it is again b minus ax m, a second norm. So we are asked how will we calculate the norm of the residual. Residual is b minus ax. So ax is equal to b. Here it was q, but let it be. So ax is equal to b or ax is equal to q. Whatever the residual is given by b minus ax or q minus ax. The norm of the residual at the end of m iteration is b minus ax at m. Ax at the mth iteration. X at the mth iteration. X only will change every time, right? So it is b minus ax at m iteration. This gives us the residual. So then how do we calculate norm? So is it largest value in the magnitude of b minus ax at m, or it is second norm of b minus ax at m? So actually both the ways can be used to evaluate the norm of the residual at the end of m iterations. So option A 1, option B 1 and 2, option C neither 1 nor 2, option D 2. So answer is option B, that is both 1 and 2 is the right answer. Norm of the residual at the end of m iteration can be evaluated using two approaches. We will see how in the next slide. So largest value in the magnitude of b minus ax at m. So this is a residual. This represents the residual for the current approximation xm after m iterations. The residual Rm is equal to b minus axm. Rm is residual at the end of m iterations. It is the vector difference between the right hand side matrix B and the result of the matrix vector multiplication axm. So axm will also give us a single column vector, and B is also column vector. So it is a vector difference between the right hand side B and the result of the matrix multiplication, matrix vector multiplication axm. A is matrix, X is the column vector. So the largest value in the magnitude of the residual Rm corresponds to the maximum absolute value of the components of the residual vector. So the largest value corresponds to the maximum absolute value for the components of the residual vector. So it is one method. This is seen as the infinity norm or maximum norm of the residual. So this is one way of calculating or representing the norm, that is maximum norm of the residual. The second one was that second norm, b minus axm at 2. So here this represents two norms or Euclidean norm of the residual vector. The 2 norm is defined as Rm at 2 like equal to sum of actually ith component of the residual vector. So it is like summing up all the component of the residual vector. The residual vector will have all the components, right? So we are just summing up all the component of the residual vector Rm. So this is the standard way to measure the size or magnitude of the residual in a more globally average sense. So both the methods, that is the maximum norm and this particular norm, both of these are valid ways to evaluate the norm of the residual after m iterations depending on the norm we are using, like it is like infinity norm or 2 norm, whichever we use we can go with that. So answer to question 13 is, the norm of the residual at the end of m iterations can be evaluated as dash. Option A, largest value in the magnitude of b minus ax m, and the second one, say 2 norm, b minus ax m at 2. So both of these are the right answer. So option B, 1 and 2 is the right answer. B, 1 and 2 is the right answer. Now we are going to question 14. In question 14, what is given is that which of the following methods will give a solution to a set of linear algebraic equations in a countably finite number of arithmetic operations? Which of the following methods will give a solution to a set of linear algebraic equations in a countably finite number of arithmetic operations? So, in a limited number of arithmetic operations, which of the following methods will give us a solution? That is the question. We will see what is given first. First one, Jacobi method. Second one, Gauss elimination method. And third one, LU decomposition method. So first one, it is I'll just switch off my camera because it is I have some network interruption. The number of equations to be solved is 60,000 A. In general, it is aptitude question. Actually, there was Adarsh Singari. I'm sorry, like, but I didn't see the chat window during the time. So I apologize for that. But yeah, thanks for answering. I mean, I apologize for not looking at the chat window during the call. Sorry, but yeah, thank you for answering. I think he left now. Sorry. Jacobi method, Gaussian elimination, LU decomposition. So option A, 1 only. Option B, 2 only. Option C, 1 and 2. Option D, 2 and 3 only. So actually, which of the following methods will give a solution to a set of linear algebraic equations in a countably finite number of arithmetic operations? So answer is um, like Gauss elimination and LU decomposition will give actually. So answer is option D, that is 2 and 3, because these are direct method, whereas Jacobi method is an iterative method. So a Jacobi method will take time to get the solution, whereas Gaussian elimination and LU decomposition will give the solution directly. So we will get the solution in a countably finite number of arithmetic operations. So, Jacobi method is an iterative technique. It does not guarantee a solution in a finite number of operations because it iterates until convergence, which may not occur in a finite number of steps if the condition for convergence are not met or if the tolerance is too strict. Jacobi method is an iterative technique. it does not guarantee a solution in a finite number of operations, because it iterates till it meets the convergence. So which may not occur in a finite number of steps if condition for convergence is not met, if tolerance is too strict. Like if we keep tolerance value very less, 10 power minus 7, 10 power minus 8, tolerance value will be very less, too strict. So that is one thing. Gaussian elimination is a direct method that transforms the system into an upper triangular form through a series of operations. It guarantees a solution in a finite number of operations, especially order of n cube. So for this, n into n system of equations, n cross n. So if we have n unknowns, we will get it in the n cube number of steps. So it guarantees a solution in a finite number of operations. So third one, it is LU decomposition. LU decomposition is another direct method that decomposes the matrix into lower and upper triangular matrices. Like Gaussian elimination, it requires finite number of operations, specifically for order of n cube for a dense matrix, similar to Gaussian elimination. So Gaussian elimination, LU decomposition method gives the finite solution in the order of n cube, whereas Jacobi method is an iterative method and it does not converge till we get the solution. Both Gaussian elimination and LU decomposition provide solutions in a countably finite number of arithmetic operations. The Jacobi method does not guarantee a solution in a finite number of approximations. So this is question 14. In question 15 we have, that is last question for today's class. Which of the following statements is true about solution of the linear system of algebraic equations Ax is equal to b with known coefficients? So we have, if Gaussian elimination works, LU decomposition can also be used. Second one, if Gauss-Seidel works, TDMA method can also be used. So this is a simple statement actually. So we are asked to identify which of the following statements are true about solving for the linear algebraic equations. First one, if Gaussian elimination works, LU decomposition can also be used. Gaussian elimination is making the matrix into upper triangular matrix. LU decomposition is splitting the matrix into upper and lower triangular matrix. So if Gaussian elimination works, LU decomposition can also be used. So one is true. Second one, it is given that if Gauss-Seidel works, TDMA method can also be used. So this is also true. This is not true. This is not true. Because Gauss-Seidel is a iterative procedure, TDMA is also an iterative procedure, but TDMA, tridiagonal matrix algorithm, requires a special criteria that it should have a diagonal element and subdiagonal element and above diagonal element. That structure should be there in TDMA method to get the solution. So we cannot say if Gauss-Seidel works, TDMA can also be used. So that is a false statement. So one is true, two is false. Option A 1. Option B 2, option C 1 and 2, option D neither 1 nor 2. So answer is, which of the following statements is true? So answer is option A, 1 is the right answer. So we'll see a quick explanation. If Gaussian elimination works, LU decomposition can also be used. Statement is true. LU decomposition is essentially a matrix factorization method that builds upon Gaussian elimination. It decomposes the matrix A into a product of lower decomposition lower triangular matrix L and upper triangular matrix U. If Gaussian elimination can be successfully applied to a matrix A, then LU decomposition can also be performed on A. Second statement, if Gauss-Seidel works, TDMA can also be used. This statement is false because Gauss-Seidel is an iterative method that works for the general system of linear algebraic equations provided certain convergence conditions are met, like diagonal dominance. Second one, in contrast, TDMA is a direct method specifically designed for solving tridiagonal system of equations. I'm sorry, TDMA is a direct method. It is not an iterative method. It is a direct method. Gauss-Seidel is an iterative method. Provided certain convergence condition is met, Gauss-Seidel will give solution. In contrast, TDMA is a direct method specifically designed for solving tridiagonal system of equations. The applicability of TDMA depends on the structure of coefficient matrix being tridiagonal, which is not guaranteed in general systems where Gauss-Seidel might work. So that is the case. So yeah, we have reached the end. Thank you for attending today's class. If you have any doubts, you can ask actually. But yeah, one thing I should say now, like anyways, like there was that one person, right, Mr. Ardhari Singari. So like I apologize for not answering your questions during that time. So after this, I'm not sure which question is coming with exact location. So if you can provide those questions in the link of the YouTube video, I'll answer. Or if you have doubts, we can clear in the next session as well. So if you come, I'll be happy to take those questions in the next class. And from next class, I will try to see the questions also simultaneously. The thing is, if I go and check the questions, sometimes my recording is being broken. So like a recording is being stopped by something happening. So because of that only, I didn't see the in call messages, and I didn't get any sounds during that time. So yeah, from next class I will try to be more attentive to the in call messages also, and we will answer those. So yeah, any number of equations to be solved is 55,000. Yeah, 55,000, 60,000. It is a general aptitude question. CA 426. Yeah, thank you. I guess it is. Yeah, we will meet next week again. Thank you, Adarsh. Sorry, it is not Mr. Adarsh Singari. Thank you for asking questions. I didn't see that, so I once again apologize. And thank you for attending. We will meet again in the next class, in the next Saturday, same time. Thank you. I am closing the session.